Okay, in this video I'm going over the Molarity Stoichiometry White Lab homework assignment. This is to prepare you for the quiz we have coming up. So question 1, what's the molarity of a solution made from 16.2 grams of sodium sulfide dissolved in 200 milliliters of water? So these are your basic molarity questions. You got to memorize the formula. Molarity, capital M, equals moles per liter. Okay, and we've talked about putting that in this triangle where molarity is moles per liter, like that. Alright, so question 1, we're looking for molarity, so we can leave the formula just like this. And we're given grams and milliliters, so we're going to have to do two conversions there. Grams are going to go to moles, and milliliters are going to go to liters. So in this problem, it gave me 16.2 grams of sodium sulfide. Again, naming is always as important as it's always been. Okay, I've worked this out, so I'll go quickly. Molar mass of sodium sulfide is 78.05 grams. Gram cancels gram. And this gives me 0.208 moles of Na2S. And then converting milliliters to liters is pretty easy. Just divide it by 1,000 or move the decimal point 3 points to the left. So that's going to be 0.200. So molarity is moles per liter, which is 0.208 divided by 0.200. And if we want to be specific with the units, it's moles over liter. And this works out to 1.04. And the unit for molarity, you could leave it as moles per liter, but the better thing is to just write capital M, and you would say 1.04 molar. Number 2, how much water do you need to add to 8.32 grams of aluminum nitrate to make a 2.30 molar solution? Okay, so this time I'm solving for the volume component. So here's my triangle. Molarity is moles per liter. So liters equals moles over molarity. Okay. So I'm given grams and I'm given molarity, so grams are going to have to go to moles, just like before. So 8.32 grams of aluminum nitrate, NO33, and the molar mass of this is 213.00 grams. Gram cancels gram. This works out to be 0.0391 moles of aluminum nitrate. Okay, so that's my moles. Molarity is given in the problem, so we could just solve this right away. Liters equals moles, which is 0.0391 moles, divided by my molarity, which is 2.30. And for molarity, I want to keep my units consistent here. Let's put moles per liter. So if you look at what cancels, mole cancels moles. Liter is like my double denominator down here. It's my inverse of my inverse. So the liters are going to end up coming up as our unit. And mathematically, this works out to, oh, come on, unfreeze. Alright, 0.0170 liters. And the problem doesn't ask for milliliters, but this is kind of a bulky way of writing it. Let's convert that to milliliters to be more consistent. So you just kind of move the decimal point 3 places to the right, 17.0 milliliters. So really either of these are correct, unless I tell you one way or the other. Okay. Number 3, calculate how to make a 100 milliliter 1.50 molar solution of copper 2 chloride. Note your final answer should state how many grams of the solid must be added to 100 milliliters of water. Alright, so in this case, again, we need to find how many grams, and since grams aren't part of the formula, we're going to have to find moles and then grams. So, molarity equals moles per liter. But we're going to find moles, which is going to be molarity times liters. Okay, so my molarity is 1.50, and let's do moles per liter for that. My liters, well, it gives me 100 milliliters, so that's going to be 0.100 liters. Liter cancels liter. And this gives me 0.150 moles of CuCl2. So that's how many moles you need. But we need to know how many grams that is. So this is just a simple gram calculation. So the molar mass of copper 2 chloride, you look it up, it's 134.45 grams. So in total, 20.2 grams of CuCl2. Or in other words, you take this mass of copper 2 chloride, dissolve it in 100 milliliters of water, and that'll give you your solution. Okay, number 4. So now we're in molarity stoichiometry calculations. The basic idea behind this is in the last unit we did things like we would say 17 grams of reactant A reacts with 49 grams of reactant B, predict the products, how much of each, so I get your limiting reactant. Well, now instead of telling you grams and grams, I'm going to tell you how many milliliters of different molarities. So you just have to work out simple calculations for that. Okay? So we have 36.0 milliliters of 0.310 molar potassium carbonate. Now, even if I don't tell you the state on these, if it has a molarity to it, like in the problem 0.310, it's aqueous. Just because by definition, the molarity is moles per liter, so it's moles of the solute dissolved in water. So this is going to be aqueous. And that's going to react with barium acetate. Also going to be aqueous because I told you the molarity. So the question says, what mass of the precipitate should form? Note, you need to use your solubility table to identify the precipitate. And you guys should know precipitate is the solid product that forms. And we have to consider which is the limiting reactant. Okay, so first of all, we have a double replacement reaction. We're going to get barium carbonate, and we're going to get potassium acetate. Let's look up these states. Barium carbonate is a solid, so there's my precipitate. And I've done these enough to just know that anytime you see potassium or anytime you see acetate, it's just going to be aqueous. But let's just double check. Potassium acetate, definitely aqueous. Okay, so we have to balance it out, and I just need a 2 here. So in other words, what I'm looking for is just the mass of this. So this isn't a problem where you need a full Mica table or a BCE table. You could if you want, you're just doing a little bit of extra work. Alright, so mole ratio, 1s and then a 2 here. So I have to find out how many moles of each of my reactants I have. So in this problem, I don't tell you grams, I'm telling you the volume of the molarity. And what you'll hopefully realize is this actually makes it easier because you don't have to deal with molar masses. Alright, so let's do the molar calculations down here, the mole calculations. So moles equal molarity times liters. I'm just rearranging that original formula. So for the first one, my molarity is 0.310 moles per liter. And my liters, it's 36.0 milliliters, so I'm going to convert that to liters, 0.0360 liters. Liter cancels liter. And that gives us 0.0112 moles of K2CO3, potassium carbonate. And for my other calculation, it's 0.135 moles per liter. That's my molarity. And my volume for that is 0.063 liters. Liter cancels liter. Giving me 0.00851 moles of barium acetate. Alright, so I found my moles, and these are going to go right up here. All right. So the next thing you have to do now is find x. Basically, I'll put my x under the precipitate. You know, you don't need to solve for the last product. But to find x, I need to know which of these numbers to use, so I'm going to need to find which is my limiting reactant. Fortunately, this is a nice, easy problem. It's a 1-to-1 ratio. They're going to be used up at the same rate, so whichever one I have less of is going to get used up first, which in this case is my barium acetate. Limiting reactant, excess reactant. Okay? So my limiting reactant is going to be completely used up, getting 0. And since we see another nice easy 1-to-1 ratio, I know that I'm going to get this same amount of my solid precipitate forming, plus 0.00851 moles. Okay. Problem asked what mass, so we need to convert this moles into grams, which I'll let you guys work out the calculations for. Molar mass of barium carbonate works out to 255.42. So my final answer for this is 2.17 grams. 2.17 grams of the solid precipitate. Okay. Number 5. You have 2 beakers. One has 1.20 molar NaOH, and the other has 0.740 molar HCl. If you pour 12.0 milliliters of the NaOH into a test tube, what volume of the HCl must you add for a perfect reaction? I should have said perfect stoichiometric reaction. What I mean by the perfect reaction is both of the reactants get used up completely. There's nothing left over. So in other words, they're both a limiting reactant. There's no excess reactant, and all you get are products. So for this type of problem, I told you that you pour 12 milliliters of the sodium hydroxide into a test tube. Now I gave you the volume and the molarity. So we know how many moles of the NaOH go in. What we have to figure out is how many moles of the other one, the HCl, are going to perfectly cancel that out. So we need to start with our balanced equation. So we have NaOH, and since I tell you the molarity, you know it's a solution, aqueous, is going to react with HCl. Again, we know it's aqueous. And let's see, NaCl and HOH is just going to form H2O, or liquid water. So this is a double replacement reaction, but it also has another name, an acid-base neutralization reaction. You take a strong base, a strong acid, you mix them together, you get salt water, or I should say salt water, and this is aqueous. Alright, so this looks like it's already balanced. Yes, it is. So we got 1s across the board. Alright. So what we're going to have to do is use math and find how much of the NaOH was added in moles. And then since it's a 1-to-1 ratio, we just need that exact same number of moles of my HCl, hydrochloric acid. Alright, so working out for the NaOH, I tell you the volume and the molarity. So moles equals molarity times liters, which in this case is 1.20 moles per liter times my volume, which is 12 milliliters, converted into liters is 0.0120 liters. Liter cancels liter, and that equals 0.0144. And that's moles of NaOH. So that's how much went in over here. Okay? And since it's a nice easy 1-to-1 ratio, in order to get that perfect reaction, I also need 0.0144 moles of HCl. Okay? But the problem doesn't ask how many moles of it you need. It asks how many, or what volume of the HCl. So this is moles. I know my molarity of the HCl in the problem. It's 0.740 molar. We're going to have to figure out the volume. So my formula goes molarity equals moles per liter. So liters are going to equal moles over molarity. So my moles is 0.0144. My molarity is 0.740. But just for the sake of units, let's say moles per liter for that. Mole cancels mole, liter comes to the top, and the final answer we get is 0.0195 liters. Or if we want to convert that to milliliters to be more practical, 19.5 milliliters. Number 6. So we're now in the White Lab Supernatant Test calculations. All right. 1.2 moles of CaCl2 aqueous are added to sodium carbonate aqueous. And we should be very familiar with this reaction by now. CaCO3 solid plus 2 NaCl aqueous. Alright, so in this problem, I gave you one step already. I told you the moles instead of the grams. So my mole ratio is 1 to 1 to 1 to 2. I did 1.2 moles of this, added to 0.82 moles of this. And I'm not asking for anything over here. All I say is draw the sketch. But you'll see why this is important. Alright, so to draw this sketch, we do beaker 1 plus beaker 2 yields beaker 3. So in beaker 1, this is aqueous. So what I have here is Ca2 plus and Cl minus. Both of them are floating around. And we have to add the waters. Now make sure when you do these ions, you separate all the ions out. I still had a lot of people that would do like Ca2 plus and Cl2. But remember, in water, those two chlorines are going to separate into Cl minus. Okay, so let's add our waters. The O's face the positive, the H's face the negative. Okay, over here, the NAs are going to split up. The CO3 2 minus is going to split up. Like this. Same deal with the hydrogen, or with the waters. Alright, and then over here, let's put our solid product at the bottom. And I actually like to put the line there to show that it's physically separated. And then up here we have NaCl aqueous, so it's going to be Na plus and Cl minus. But we're not done yet. We also have to include the excess reactant floating around. So this one's pretty easy. We could see, since we have a 1-to-1 ratio, and we had more of this than that, this one is going to be my limiting reactant because it's going to run out first, and this is my excess reactant. So this stuff is going to be left over in what's called the supernatant, which is this. So let's add calcium and chloride ions. Now you already have chloride, so you can rewrite it if you want, but just to save space, I won't. But I do have to add the calcium, like that. Okay? So this is an accurate representation of what's going on. We form chalk on the bottom, we have my aqueous product here, but we also have the excess reactant left over, which is calcium chloride. Do not put any carbonate in here floating around, because it got totally used up. All of this carbonate is now locked in place down here. Okay? Number 7. Okay, so we are using the math here. In the reaction above, the group collects 62.3 grams of the solid precipitate, which is the chalk, calcium carbonate. What is their percent yield? Okay, so for this, we're given the actual yield. We need to find the theoretical yield, or in other words, we need to find mathematically how much they could get in theory. So let's figure out the theoretical yield. As I said, this is my limiting reactant, so this is going to get totally used up. Okay, this is a 1-to-1 ratio, so they should form 0.82 moles of CaCO3. So we just need to convert that into grams, and we're almost there. So let's do number 7. So, oh, you know what? I forgot to do number 6 was the supernatant test. can do that over here. So for this, let me just rewrite my beaker over here. So I had CaCO3, I had Na, Cl, and Ca. Now just for time, I'm going to ignore the waters here. So the supernatant test, you're going to add both of your reactants to the supernatant. Now remember, this is your supernatant. Super means above, so supernatant is the liquid that is above your precipitate, and that is our precipitate. All right, so supernatant test number 1, adding CaCl2, but it's important to note here, this is aqueous. So really, I'm not really adding calcium chloride, because that's that white salt that you guys use. I'm adding a liquid that contains calcium ions and chloride ions floating around. So when I add this to this, is anything going to react? Now, in this case, when it reacts, I mean it's going to form my solid precipitate. So will anything happen? And the answer is no, because look, I already have calcium floating around, I already have chloride floating around. So no, you're not going to see any kind of reaction because you already have both of those ions floating around. No reaction. Second supernatant test, adding Na2CO3. Okay, so adding Na, no effect because we already have Na floating around, but adding CO3, and again that has to be aqueous, when I add the carbonate ion, those carbonates are going to find this calcium and they are going to react. Okay, so because I don't have carbonate, the calcium carbonate are going to react. So yes, reaction. All right. Back to number 7. So we found that it's going to form 0.82 moles of CaCO3. We just need to convert to grams. Molar mass is 100.09 for chalk. Grams per mole, which works out to 82.1 grams of CaCO3. So that's my theoretical yield. In theory, you could possibly form that much. How much did they actually get? Well, according to the problem, they got 62.3 grams. So when we work out this math, it comes out to 0.759 or 75.9% yield. Okay. Last problem, number 8. So this one's putting it all together. My suggestion, if you have not done this problem yet, take 10 to 15 minutes and do the full problem, then check the video. Number 8. Alright, so this is another white lab calculation. I tell you the volume of each and the molarity of each. So let's start with our balanced equation. CaCl2 aqueous plus Na2CO3 aqueous yields CaCO3 solid plus 2NaCl aqueous. Well, in this problem, we have to find how many moles, okay, because letter A says complete the Mica table or the BCE table. So that's mole ratio, initial, change, and after. So the mole ratio is 1 to 1 to 1 to 2. So we have to find how many moles we initially have. All right, so our formula is moles equals molarity times liters. Again, you just rearrange the molarity formula to find that. So for my calcium chloride, it's going to be 0.750 moles per liter. That's my molarity. Times 25.0 milliliters, which is 0.0250 liters. And that's going to equal 0.0188 moles of CaCl2. You work out the same thing for Na2CO3. It's going to be 1.30 moles per liter times 13 milliliters, which is 0.0130 liters, and that works out to 0.017. My answer key got cut off on the side, so I need to actually do the math. 1.30 divided by times 0.013. Well, according to this, it says 0.016. Now, let me just double check my numbers. Oh, I see. My molarity is off. That should be a 5. 1.30 times 0.0135 gives me 0.01755, so 0.0176 moles Na2CO3. Okay? So these go right into my initial. Okay? Now at this point, well, we have 0 of this and 0 of that. We need to find which is my limiting reactant, and since these are a 1-to-1 ratio, it's just going to be whichever one I have less of, because they're going to be used up at the same rate. So clearly this is going to be my limiting reactant, and this is going to be my excess reactant. So limiting reactants gets completely used up. And let's see how much of this gets used up. It's not the full amount, but look, it's a 1-to-1 ratio, so we can just subtract the same amount, leaving me with 0.012 moles. Okay. Note you're not going to keep your third sig fig here, because when we subtract, do we keep that sig fig? Nope, we do it just like this, the 2 sig figs. No, I think I forgot an extra 0. Sorry, one sec. 0.0188 minus 0.012. Can't even read my own writing. 0.0188 minus 0.0176. I did forget the 0. That's what happens when you go too fast. Alright. So, 2 sig figs, just like that. I mean, this isn't really... Well, I guess I did ask for the mica table. I didn't ask for grams, though. Let's see how much chalk we form. So, it's a 1-to-1 ratio. So, for every mole of this that we lost, we're going to gain 1 mole of that. So, it's the exact same number. 0.0176. And this is a 1-to-2, so we're just going to double this and write it over here. So that works out to 0.0352. 0.0176. Okay, so that is my mica table is complete for this reaction. Alright, letter B. If 1.40 grams of the precipitate is recovered, so that's the actual yield, what's the percent yield? Well, in this problem, I found that this many moles of the precipitate, solid, should have formed. We need to convert that to grams, and that's going to tell us what mass of it should have formed. So, this times my molar mass, which is 100.09 grams per mole, equals 1.76 grams of CaCO3. So that's my theoretical yield. That's how much could form in theory. So letter B is my actual yield, 1.41 grams, divided by my theoretical yield, 1.76 grams, which equals 0.801, which equals 80.1% yield. Okay. Letter C, I'm asking for the sketch of the reaction. So beaker 1 plus beaker 2 yields beaker 3. Alright, so my original reaction was CaCl2 plus Na2CO3 yields CaCO3 plus 2NaCl. Aqueous. So, same as before, we have calcium ions and chloride ions floating around. We have sodium ions and carbonate ions floating around. We have CaCO3 solid at the bottom. We have sodium and chloride floating around. So those are just my initial ions. Let me add some waters. okay? But we're not done yet. I also have to add my excess reactant to this. So, according to my problem, my excess reactant is calcium chloride. So we're also going to get calcium chloride floating around inside this solution. So I already have the chloride, let's add the calcium. With a little bit more planning, I would have made it so that it was the other way, but you get the picture. Obviously, if this was the limiting and this was the excess, we would have carbonate floating around in here. Okay, so that's my reaction. You could add more waters if you'd like, and at the bottom, you could write that statement about the law of conservation of mass is not followed. And finally, letter D. Predict the supernatant test. So let's draw my supernatant one more time. Here's my CaCO3. That's not the supernatant, that's the precipitate. My supernatant is my aqueous product, which is NaCl, split up. And it's also my excess reactant, which is calcium chloride, split up. And with waters in here. So, supernatant test number 1, adding CaCl2 aqueous. Are we going to see any kind of reaction? Well, just like before, we're adding calcium and chloride ions. We already have calcium and chloride ions, so we're not going to see any kind of reaction. Remember, in order to see a reaction, you need some kind of solid to form. In the case of the white lab, that solid is going to be chalk, so you need calcium and carbonate ions to meet and form chalk. Supernatant test number 2. Adding Na2CO3 aqueous. Well, now the Na is going to have no effect because we already have Na, but the carbonate is going to find the calcium and it's going to form calcium carbonate or chalk. So yes, we will see a reaction. And that's it. Okay.